Okay, so today my plan, да, можно проверить, что в эфире.
Да, но снова в маленьком экране.
Ага, да.
Звук тоже есть еще.
Да, звук слышно.
Должны переключиться. Да,
Okay. So today my plan is to discuss field theory at the beginning of the field theory of algebraic extension, and here I want to remind a few properties. So first of all, what are separable and normal extensions? So of course, and what are Galois extensions? As I understand, you have heard of this. Raise the hand. If yes, yeah. But I do not know exactly how you heard it, and that's why I want to have a short explanation or short reminder, because what we shall need is we need to understand all notions in terms of theory of embedding. So. Да.
Там, может, стерка лучше пишется.
Да, наверное, так. О. Normal separable extensions. So, how we define normal and separable extensions? First of all, we recall the following. So, we start with a field K, and we can consider algebraically closed field. Yes, or algebraic closure. So, is a field. So, we can pass to algebraic closure. So this is all solutions of all solutions of algebraic equations with coefficients in K. And also we noticed that if you take this is more or less similar to what we have discussed about integer extensions. Notice that integer extensions are particular case, yeah, because of algebraic extensions. Yeah, or if you walk over the field, you may just divide by the highest coefficient to obtain coefficient 1. Yeah? And also we may notice that if you already extend your field, so if this is algebraic extension, so all elements are algebraic in K in E. So if it is algebraic, она не везде хорошо как-то пишет, эта стерка. Extensions. So if this is algebraic extension, then its algebraic closure coincides with algebraic closure of Q. So this because the composition of algebraic extension is still algebraic. And then one can consider the following problem. So suppose you take E and take algebraic extension over K. Yeah. So so we can embed it into algebraic closure of Q. And here you will consider even not algebraic extensions, but finite algebraic extensions. So the degree of E over K is finite. Yeah. So E is over K is just a dimension of E over K. Yeah? So when you consider such thing, so you may think you may fix this particular. So notice that when you consider algebraic closure, this is not canonical object. So meaning that you are constructing it by the choice. So how you generally do it? So you pick up K. So you pick up a reducible polynomial, and what you do? You add a root. So via procedure. So if you have f is irreducible, so over K. So let us write down this as a reducible polynomials over K like this. So this gives you the possibility either to consider add a variable and take a quotient by the ideal generated by f of x, and this will get if the polynomial is irreducible, this ideal will be maximal, and what would you obtain is the field. And this this can be viewed as adding a root of unity. So adding a root of the polynomial. So if you think of this, so just x under this homomorphism maps to the corresponding root alpha. So to the element alpha of the field, and this gives you this kind of thing. And of course, if you already know that your field K sits inside algebraic closure, the polynomial can have several roots. But so the operation of choosing, so if that means that when you already put inside K inside K, then it has several roots, and then you can distinguish them, and you can start adding them in some order. And this adding roots in different order may give you a different result, but the result will be isomorphic. So so notice that any homomorphism of the field is embedding, of course. So homomorphisms of the field in any field f is embedding, since kernel is kernel is ideal. Non-trivial ideal is not, if this is not embedding. So if moreover you have the following proposition, notice that the motivation of this, yes, so you can consider the different embeddings, yes, so just and consider a set of embeddings sigma of E inside the algebraic closure but of course, so embedding is rather, it is somehow relative thing. So because if I mean because when you are considering extensions of K, it is reasonable to and K is sitting inside K bar. Yeah, so we are thinking about E. As you start with K and add some variable, some elements of K bar. And this means that this embeddings, yeah, so since you are thinking of this situation like this, yeah, so this means that these embeddings are identity on K, yeah, so this sigma, so it is a map, it is homomorphism, so sigma on K is just the identity map, the map you start with identity on K, so identical embedding of K into K bar. Yes, so notice that K bar comes, the construction of K bar comes intrinsically with K. So this the number of such embeddings is called separable degree. Yeah, so number of embeddings is called separable degree. And denoted like UFS, meaning for separable. Yeah? So now we should just say something about separable degree. And the main thing about separable degree that we shall use, that separable degree doesn't depend on the choice of algebraic closure. So claim that separable degree does not depend on algebraic, on choice, yes, so on the choice of algebraic closure. Yeah, so here in this setting we should understand that any algebraic closures are isomorphic and in some sense consistently. And this will be done as follows. So first of all, lemma So we shall prove this claim. Well, I do not prove the existence of algebraic closure, yeah, because naively it is just adding more and more elements which are roots of polynomials and checking that you still have algebraic extension, and the limit of such algebraic extensions, finite algebraic extensions, give you this inseparable algebraic extension. But of course, this construction you should be careful about that, because you can have, if you have countable number of elements in the field, that's okay. Yes, so you just can enumerate. If not, you should use some kind of Zhgun lemma. So, and here it will be the lemma. Yeah, so that also uses Zhgun lemma. It says that suppose you have embedding of E inside the algebraic closure of K extends sigma 2 embedding. So suppose that E itself sits in its fixed K inside its algebraic closure. E is algebraic extension. And also take algebraic extension of algebraic closure of E, algebraic so it is to say that it is, I mean, of course it will be also algebraic closure of K, but sitting inside K, yeah? So this extends to maps of, so embedding of algebraic closures, yeah? And this is actually isomorphism of algebraic closure. So isomorphism of E bar inside K bar. Extending, yeah, so extending E, yeah, so just extending sigma. So, this also, so let me do some sublemma, which is easier. So this refers to precisely isomorphism. Yeah, so now, so let me say something about extension, and then I shall also say about isomorphism. So, first of all, so how to prove such statement? Yeah, so this should be just instead of so you should work with possible pairs. Yeah, so for possible extensions. So suppose, so here you have inclusion, and consider the pairs EI, so E tilde, so set of pairs. So of E and sigma tilde, so where sigma tilde is of course inclusion of E tilde inside K bar, yeah? And here you should, so this set of pairs, so when we're speaking about Zorn lemma, so you should have the order on the set. So it has, this is naturally ordered set. So that means that one map extends the other. So one map extends the other. And you can apply Zorn lemma, so meaning, so of course E tilde should be algebraic. Yes, so we should leave in our class. Yeah. And one, of course, considers maximal extension. Yes, so you do in Zorn lemma. So there exists maximal extension. E tilde that extends this map, and of course everything is of the form of the beginning picture. So the if E tilde is not K E bar, yeah, then there exists element beta that doesn't belong to E tilde, and the beta is algebraic over E. Yeah. So this means over E tilde. So or over E. So that doesn't matter. So let me put it, for example, over E. Yeah. So and if it is algebraic, it is a root of. So this means that. Beta is a root of irreducible polynomial. And it can be thought of a reducible polynomial over of course, K. Yeah, so that means, so we know that beta is algebraic over K. And irreducible polynomial over K. So we can pick the root and K bar and write down this map. Yeah, so you pick root in K bar. Yeah, so sorry, beta is, sorry. So beta is algebraic over E, and yeah, so and and of course E is contained in K bar. Yeah? So E is contained in K bar, so you are E tilde, yes, so over E tilde, and you are mapping it to the new element that doesn't already belong to E tilde, yes, so pick a root, so F, so root of F in K bar, and map. So root, so call it beta, so call it alpha, and map beta into alpha. Map beta into alpha, and that will extend. So you will have homomorphism that extends this embedding of E tilde in K bar. Yeah, so simply because so you will have. So how do we see it? simply because you have a map of E tilde x. Yeah? So we map it, we construct a map to k bar and map x into beta. And this map factors, since it maps x into alpha, so we have denoted by alpha. And this map factors through E tilde x modulo f, because f of alpha is the root. And this gives you the maps and gives you the required extension. Yes, so this is very easy but important. So this tells you that whenever, so as a corollary, if you have two algebraic closures, then they are isomorphic by this constructed isomorphism. So corollary, yeah, so also we need a small addition. So we proved this, but we also need small additional lemma. Suppose you have an automorphism of algebraic extension, so sigma maps E inside E, where E is algebraic extension. Of K, and then sigma is automorphism, so it is injective, but so this is homomorphism. But then sigma is just automorphism. So the surjective map, yes, so not only injective, but also injective.
So sigma should save k, yeah?
Yes, thanks. Yes, so, yes, sigma on k is identity. Huh? And this is also more or less clear, but really algebraic, algebraicity is important because actually you may, for example, when you have characteristic P, yeah, so who can give example of this?
One's not after automorphism.
Yeah.
Something like Frobenius?
Yeah, it's Frobenius, but on which field? Yeah, so you, I mean, on finite field that is automorphism, but so the easiest example where Frobenius is not automorphism is k of x. Yeah? So when you add one variable. So when you add one variable, then it maps to x to the power p, yeah, so it maps to the subset k of xp inside k of x. For example, k can be so we know that. So k can be taken to the finite field here. So we know that to see that coefficients really preserved. I mean, this is just example. Yeah. So or if, yeah. So here, so we take f. Yeah. So sigma and example when lemma doesn't hold. Yeah? And this allows you to, how we prove lemma very easily. Yes, so you should prove so you use algebraicity. So you should prove subjectivity. Yes, so if you have beta inside E, it is notice that we do not consider finite algebraic extension. We consider any algebraic extension. It is finiteness is not needed here. So B inside E is algebraic over K. Over K. Then it is a root of some polynomial f of x is a irreducible polynomial over K. And here you can do the following. Here you can consider some field of the in E of the roots of f of x. So take f, big F, field generated by roots. Roots of f over k in E. Yeah? And notice, of course, that this is finite dimensional field. However, the dimension is not, of course, the degree of the polynomial. Yeah, but how we can bound this field?
Degree.
Factorial, yes, because let me remark that degree of f of this field, degree of f of k is bounded by factorial of degree of f. And this is due to the fact that you are starting getting the roots of f, but on each step the irreducible polynomial should divide f, but on each step it becomes smaller and smaller. So that means that this degree doesn't probably divide this factorial of the degree, but definitely smaller. Yes, so you start adding f. First we add alpha as a root of f, then we take f, decompose it into reducible polynomials over our field where you added your root alpha. Yeah, then you take alpha 1 is a root of f1, so this is irreducible decomposition. Then you take the root of f1, then you decompose f. So you have to add all roots of f, yes, so further. So you decompose f over k of alpha 1, etc., alpha 2. And you proceed until you get all divisors, and on each step you can bound your. So here you of course decompose f1 over these guys, and then you have to decompose all other devices. Yeah, so this, yeah, however, it is, so here from the construction, it is so not so evident, yes, so that this is bounded by factorial of degree. Yeah, because you should add the roots. So here on this step you have added alpha, and you have added the root of f1, and then look of the composition of just decompose f1 into f1 tilde, etc. f2 of f2 tilde, and fk you decompose of you decompose in the corresponding irreducible elements, and then you have to add actually roots of f1, and then apply this procedure to the remaining polynomials, the f2, etc. But you are doing the induction on the sum of degrees, and sum of degrees of this factors is equal to degree of f. Yes, so that you can prove this by induction. Yes, so exercise is to prove this proof by induction. So so when you are, so when you have constructed this polynomial, this means that beta, this beta, root beta, root of f, and automorphism. So if you apply sigma beta, it is also a root of f of x. So beta is also a root of f of x. And this implies that sigma of beta belongs to this extension. And this means that sigma maps extension into itself. And now how we can argue? Yes, so so in order, so we have to prove subjectivity. Yes, so we have to prove that beta will be covered. Yeah, so beta is the element of f. Sigma maps f into itself. We have to understand that this is really isomorphism. So, but notice that f is a finite dimensional space, dimensional over k, and lemma from linear algebra, if you have a map between vector spaces of the same dimension, well, of the same vector spaces. So linear map. So let me just. Then, if it is injective, if we don't leave, it is bijective. So A is injective if and only if A is bijective. Is bijective and if and only if it is surjective. Yeah? And the reason for that that you can consider kernel and image, yeah, so that and the dimension of image is just the dimension of E. So dimension of image of dimension of image of A, yeah, is just dimension of E minus dimension of the kernel of A, yeah, since image is isomorphic to V modulo the kernel. And you see that this is less or equal than dimension of V, and if you have two subspaces of the same dimension, they coincide. Yes, so when kernel is zero, then dimension of im of A is equal to dimension of E. Then image of A is equal to E. And vice versa, if dimension of image is everything, then the dimensions coincide, then kernel is zero. So this lemma holds very easily. So if f is finitely dimensional over k, then you have inclusion, then sigma is surjective, is bijective then by lemma. So sigma is injective as the map of fields. It is bijective by lemma. So this means that sigma is isomorphic, bijective, and then this means that we have found the element from your field that maps to beta. Yes, so something so there exists beta tilde inside f such that sigma of beta tilde maps to beta. Yeah? So this is what can be thought about, yeah, and this as the result, yeah, so as the result, this means that if you have maps of algebra, there is always isomorphism of algebraic closures, yeah, so if you have different algebraic closures, so different algebraic closures are isomorphic. Yeah, so and more generally, so this means that when we fix embedding, yeah, so Yeah, this is by the second and the first lemma. Yes, so by the first previous lemma there is a map. Yes, so between algebraic. So if this is algebraic closed map, then algebraic field maps to algebraic closed field. This map extends, and by previous lemma, if you know that it is a map of algebraic field to itself, then from algebraically closed field to so from algebraic field to itself, this is just isomorphism. It cannot be inclusion. And so if you have k also you start with algebraic closures, and you have now extension of E over K. You may think of extensions, so you have two inclusions of K into K bar, and you have this so you have two inclusions, and you have a set of embeddings of E1 into K1. Yeah, so the set of embeddings of E to K1, yeah, maps under the identification of the algebraic closures to the set of embeddings of so sigma that is fixed on A. So sigma on K equal to identity on equal to the map of f of K to K1, yeah? Fixed map. Yeah, so this maps by tau, that is a map of algebraic closure, to the set of such embeddings. Yeah, so maps to the set of such embeddings. Embeddings of E into K2 by composition. And but notice that it is clear that different maps map to different maps, so this is injective map, but it is not so clear that it is surjective, and subjectivity is actually a previous lemma, so this map is clearly injective, because tau is bijection on the set of fields, so maps different map to different, but it is surjective so since any inclusion of E into K2 extends to the map of K1 to K2. Yeah. So by previous lemma,
Can't we say just if we have some map from E to K2 bar, then we can composite it with inverse to tau? And
Yeah,
we get a
it's-
map.
Right.
So we say it like that.
yeah, just, ну да, там, ну да, две стороны.
Something.
Но чтобы тау построить, вот нам все равно нужно вот это. Вот. Yeah, so by previous lemma or by or, yeah, so we shall need also that any embedding can be just prolonged to so any embedding can be prolonged to the map of algebraic closures. Yeah? So subjected by previous lemma, since for any tau, so for any eta from E into K2, there is a map extending yeah, so yeah, maybe I should say it as the remark, not the remark. By previous lemma, so there is a map. There is a map at the tilde that extending eta at the tilde is the map from K1 bar to K2 bar. Yeah? So this shows you that separable degree is independent, and now we can define separable more separable extension. So and in order to do it, we have to obtain inequality. Yeah, so just a proposition that if you have E extension is divisible by separable degree. So it is divisible by separable degree. And this follows from the following observation that actually both things are multiplicative. Yeah, so this holds from proposition. First of all, multiplicativity of the separable degree under taus. So suppose you take E, take K, and take F. So then we have separable degree of K over F is equal to the product of K over E, separable degree times separable degree of E over F. And the same holds for degree. Yeah, so the same. For usual degree. So this thing is that just is the following, that так. Yeah, so this is rather easy. Yeah, so because if you have so you have K, you have E, and you have F, and you are recalling that you are making this to algebraic closure of F. Вот, здорово, жирно, да, что как раз алгебраическое замыкание, оно большое, да. Вот, сейчас. Yeah, so you have the map that extends E, and you have inclusions of k into F, yeah, and you notice, so what you can do with inclusions over F, you can think of you can restrict them, so you take sigma and tau here, yeah, so two inclusions, and sigma and tau are equal when you restrict on F, but they could be not equal or not equal when you restrict it to E. So then you just take sigma restrict to E, so and you consider classes then the number of pairs with the same restriction so a number of inclusions of sigma E inside the of k inside F. Number of sigma k inside F bar. So with same restrictions, so such that sigma restriction to E is equal to tau restriction to E of fixed tau, this is just this separable degree k of E, yeah. And here we see that, yeah, so we do not care which, yeah, so what is inclusion of F of E inside F tilde, yeah, so this, notice that the degree a priori could be different for different tau, but we know that it is the same for different tau. So this degree does not depend on choice of tau, does not depend on choice of tau. And then you just take what is different ways to pick tau and these restrictions, and so choices to pick tau are just I mean, let me put it tau 0. Yes, sorry, make me better to write it down like this, like for fx tau 0, maybe let me put sigma here and tau here. So for fixed tau, where tau is embedding of E into f tilde, and of course here so choices to pick tau are the separable degree of E over f. And yes, so that since so over tau, so you have E over f choices for tau, then you have choices of extending tau, and the choices of extending tau are always the same due to what we have discussed so far. So this implies that this multiplicative property, the number of possible sigmas are just number of possible extensions of e to k times the number of possible extensions of f. And this yeah, so yeah, and now we can discuss the elementary extension, and then now let us prove divisibility. So proof that degree, usual degree is divisible by separable degree. And this is done in 2 steps. So first is how we can prove it. So we can check it for elementary extension. Yeah. So elementary extension is adding one element, and then we do by multiplicativity. So remark. So let me put it. So suppose you have a chain of fields. E1, E2, maybe increasing, yeah, so. Here. E1, extending f, E2, etc., ek, extending f. So such that at each step you raise ei over ei minus 1, Yeah, so f, for example, is E0. Yeah. So ei over e minus 1 is just, this extension is obtained by adding a new element, yeah, so alpha I. Yeah, so for some alpha. Algebraic. And then you see that that your separable. Suppose we have proved it for elementary extensions. So suppose we know that E over F is divisible by E over F for elementary extensions. Yeah, so then you see that this means that degrees over E I, yeah, I minus 1 are divisible by AI minus 1s, and this means this means that degree of E over F is a product of these degrees. Is a product of this EI minus 1, and this is divisible by separable product of corresponding separable degrees, and which is equal to the separable degree of the extension. And for elementary extension, it is very easy to check because what you have, you just set of embeddings, of E over F of E alpha. Yeah, so when you add the F one element, yeah, to the set of embeddings, yeah, so alpha is a root of F irreducible polynomial, and what options do we have? So alpha can map only to alpha maps to beta, where beta is a root of F. So alpha maps to beta inside f bar, so where beta is a root of f. And the number of roots is just, so the number of embeddings is just the number of different, so the number of embeddings. Is the number of distant roots. Yeah? And this is actually less or equal than the degree. Yeah? So at least if you want to prove rather just inequality, so we're already done. In order to prove divisibility, we should analyze it strictly further. Yes. So first of all, suppose so this depends on characteristic now. Yeah? So suppose you have characteristic 0. So can polynomial can a reducible polynomial have multiple roots? Why? Yeah. So if alpha is multiple, yeah, then alpha is a root of derivative. Yeah. So alpha is a root of derivative. And yeah, so just it is a direct check. Yeah, so by writing down x minus alpha k times g of t and taking the derivation. And this means that f prime, so it is smaller polynomial than f. So that means that just alpha is a root of greatest common divisor, f of x and f prime of x. But this should be 1 because alpha is minimal polynomial. Yes, so that just since f is minimal polynomial for alpha, and that implies that it divides alpha. Yeah, divides f prime. Yeah, so f divides f prime, and this can be only if f. So a polynomial of larger degree can divide the polynomial of smaller degree only if f prime of t is 0. So degree of f bigger than degree of f prime. This implies that f prime of t is identical to 0, and this is not possible in characteristic 0, and yeah, so but in characteristic p it is possible. So not possible in characteristic 0. And how does our polynomial look if this is identical equal to 0? Yeah. So so derivative looks like if your polynomial looks like AI Ti, yeah? So f prime of t looks like I AI Ti, yeah? And this means that if it is equal to 0, if and only if, all AIs are, just the AIs are not equal to 0, so all non-zero AIs are divisible by P. So if I is divisible by P for AI and that are not equal to 0. So our polynomial can be written simply as, so f can be written as the sum of PI's, well, PJ's, let me do different thing, that's PJ's. So where you have a sum over J. So the polynomial, so this means that non-separable polynomial should have the things like this, and if you think on K bar, so over F bar, if you consider this polynomial over F bar, or then you can extract the root of unity of any coefficient. So there exists so over F bar, or if F so if over the field which is perfect. Perfect means that precisely you can extract the root of unity. So over root fifth root. So over F we can extract, find B J's, so such that Bj in the power P is equal to APJ. Yeah. And this means that you can write it down as the sum of J power times T J in the power P, which is just the raise of F in the power P. And you see that this, then you can proceed with this polynomial further, and you see that so you end when your polynomial becomes separable. So you consider this is you consider the sub-extension. So where you add this piece roots of unity, and you see that number. So you end when the end procedure. Until we cannot reduce this reduce. So meaning that derivative is non-trivial. If so on the so derivative is not identity to 0, so polynomial has distinct root.
Why isn't already contradiction. Isn't f should be reducible?
Yeah, you mean after this thing, yeah?
No,
But
before.
yeah, before. So here it is reducible, of course,
Uh-huh.
in the beginning. But if this is not reducible, then you just apply it to you decompose it and just apply it to irreducible.
Yeah, but we construct f as an product of some other polynomials. Isn't we what?
Yeah, I mean if this is reducible, yeah,
Yeah.
over the field that we consider, then it is you have yeah, so there is
По-другому немножко.
Да, мне уже просто я не понял, то, что это же мы над замыканием все делаем.
Да, это, в общем, как бы там, где, ну, это уже над замыканием. То есть, как бы, ну и пока мы, то есть это мы делаем сразу, ну, за один этап. То есть, как бы, мы на самом деле, ну, то есть, как бы это, so this procedure is not step by step, yeah? So actually this procedure is the following. So knowing that this holds, the coefficients are divisible, we just divide it by the highest power that we can do, yeah?
Mhm.
So formally we have to do the following. So take highest power, take k so highest power such just the I is any I with AI is not equal to 0 is divisible by p to the power k, yeah, and then you are putting pk over and consider the pk roots, and here you consider pk here and pk here, yeah. So yeah, so that you see that this polynomial is not identical to 0, so it has distance. So this is just, let us put it g of t in the power pk. So g of t is the derivative is not identical to 0 because these are not divisible. There is not divisible coefficient. So since there exists b j not 0 with j is not divisible by p. And this implies that this polynomial has distance 0, so just, and of course, yeah, so this implies already that so this implies that the degree of f is divisible by this inseparable, this divisor, so the number of inclusions is just the degree of distant, number of distant roots, so g of t, yeah, so the number of inclusions of E f of alpha over f, separable degrees the number of inclusions of f of alpha inside f bar, and this is number of distant roots, so this is degree of t, so number. This is already done in Kiva. So this implies that this degree is, yeah, so the number of degree g of t. So this means that that divides the degree of f, and it is so it has also the corollary that the number after division you get fifth power, yeah? So that the number after division, so corollary of the statement that you can divide the usual degree by separable degree. This is called the inseparable degree. Yeah? And denoted by I, and this is power of p. Yeah, so notice that I do not claim that this is full power of p. So this is not possibly maximal power of p that divides your degree of extension. Yeah, because so example of this. So who knows? Example.
It's only over a finite field. Yeah. Well,
example. Yeah. Finite field, the degree of the extension.
well, I mean, it's only for fields with finite characteristic. With characteristic.
Yeah. So example is that you can have x. So you can take solutions of the following equations. The so-called Artin-Schreier equation, and one can prove that. Yes, so notice that here the maybe you better to put minus here, so technically. In characteristic P. So here you see that this degree is divisible by P, yeah? But notice that so here the reason that this thing is good that you have automorphism, natural automorphism, that if you have alpha is a root, then alpha plus 1 is also a root. This is because raising to 5th power is homomorphism. Yeah, so you add 1 here, and here it is just x plus 1 in the 5th power minus x plus 1, and well, alpha plus 1 plus e, and you see that this is just alpha p plus 1, and you subtract and you get the same thing. Minus 1 plus 3. And this is so if you take all possible numbers, yes, so you have if you take alpha plus I, it is also a root, and the I runs through from 0 to p minus 1. Yeah, so this implies that given one root after applying automorphism, you get all roots, and this gives you that if you have already one root so this gives you that there is automorphism that is acting transitively on the set of roots, so the polynomial should be reducible over the field. So this proves that this polynomial is reducible, because if you have automorphism of the field of the polynomial which is not irreducible, then each irreducible factor maps to its irreducible factor. So that means that since so let me call it sigma acts transitively on the set of roots, of f. So this implies that f is not f1 times f2 for irreducible factors. Since sigma should preserve them. Yeah, because sigma, if this factor has coefficients in k, yeah, so then sigma preserves. So and also notice that so one remark that also will be is important. So in characteristic P, extracting pth root is so I want to remind then if you have characteristic P, then operation of extraction of the root of A maps to 1P is it is unique. So there is a unique way to find beta, so B, that solves this equation. And the reason is very simple. Why?
What do you mean с unique?
Ну, то есть просто вы можете для любого А найти единственное B, такое, что B в степени P равно.
Почему B в квадрате не проверено?
Нет, P степень. Ну тогда А будет в квадрате.
Сейчас.
Ну, у поля элемента.
Ну да. Почему не можем умножить на какой-то корень из единицы?
Ну, потому что как раз, ну, это есть p корень из единицы, но p корней нету из единицы. А почему? Ну, это как бы проще, просто смотрите, ну, как бы, что такое, вот, so what does it mean that, so p is characteristic, yeah? So if you have two solutions, v1 of the same equation, then you can subtract them.
And you get 0.
So this means that yeah, this is just because Frobenius, actually this map is Frobenius, is homomorphism. Yes, so that means that you can write down as follows, and it is a minus a, which is equal to 0. And the reason for the, just that piece power, yeah, and piece just the reason is simply that you have a field, you have power of Frobenius here, and this is a injective map because it is, so of course this is no potence, but this is injective field for injective map for fields. Of course, if you require that you do not have a nilpotence in the algebra, you will also have this no nilpotence, or even more stronger p nilpotence. Okay, so let me do the break. Sorry for overtime. Then after the break, we shall discuss separable and normal extensions from this point of view of embeddings. And so, sorry for just I realized that I said a different thing here that I wanted to say. Yeah, about the separation. Yeah. So precisely about the separation. This is just. I mean, this. I just consider this as the remark. Yeah. So yeah. So just that was precisely. About your question during the class. Yeah. So just I made the different, precisely opposite thing that I wanted to make here. Yeah. So the problem is that when you this is just so this is operation that you can do when coefficients belong to the finite field or to more generally they belong to perfect field, so the field where you can extract root of unity. But in general, you should do not precisely not this thing, but simply a more simple thing. Yeah, so you just have to write down f.
So what do you mean by perfect? Isn't in algebraic extension, in algebraic closure, there is always
yeah, it's always yeah. So there is always
yeah. So what's the problem?
But so what I wanted to say that you just can do the following. So you can simply write this polynomial of g of t. So where you add the variable is raised to this power. Yeah? So nothing too clever. Yeah? And then this means that over. So if g is of course irreducible here. Yeah, just because it is. If g was reducible, so here it is clear that g is irreducible. So g is irreducible, and has no multiple components. has no multiple roots. So since we have taken maximal k, and so since g of t derivative is not equal identically to 0. Yeah?
What's the difference with
So the
the
difference
previous one?
that I have taken gt into the pth power.
Yeah.
And here I take the same coefficients. So in order to put the gt, I mean, in order to do that operation I have done, I have abstracted roots and put it as everything is raised to the pth power. But for this operation you have to extract roots of coefficients. But then you lose control on the polynomial in the brackets. If the coefficients doesn't belong to basic fields. And here I have taken, so I have put t inside the polynomial. So here it is clear that g is irreducible, because otherwise you have reducibility of f. And here it is equal that derivative is not identical to 0, yeah, just because we have taken such k. Yeah? And this is the choice of k. So by choice of k. And yeah, so you this is a little bit irrelevant. And now, yeah, so now you we're using the following, that so the field can be thought of extending. So but now we shall use the injectivity of the extracting pth roots. So this is actually needed. So this observation. Yeah, so notice that now your extension, so beta can be just. А что у нас корнем было? Тут мне просто не помните? Ну ладно, уже подвинул. Секунду. Кажется, мы, наверное, вообще никак не узнаем. Альфа, да? Ну, как бы исходное расширение альфа. Yeah, so put beta is a root of g. So beta is a root of g. And then alpha is just extracting, so then alpha, which is root of f, it is just extracting kth power root of beta, yeah? And alpha is for each beta, alpha is unique. So for each beta, alpha is unique. So this means that, yeah, because there is unique as we have discussed. There is unique choice of extracting beta. So if you have embedding, so when you have embedding beta, so this implies that embedding beta, f of beta inside the f bar, sigma induces, so it lifts to unique embedding of alpha, f of alpha, lifts to
Shouldn't it be otherwise
Unique.
half equal to beta to the power of pk?
нет, but корень именно g, да, поэтому альфа корень вот этого, поэтому если мы подставим вот сюда альфа, то мы бета даже сделаем. Вот, сейчас. So it is unique. A lift to unique root. So unique embedding. F of alpha inside F bar. Yeah? So choice of embedding beta lifts to unique embedding of alpha F bar. So this means that the number of embeddings of F alpha is equal to the number So the number of embeddings is equal to the number of embeddings f of beta inside the bar. So which is the number of roots? So of G, so the number of distant roots of G. So, and this is not equal to degree of G. Okay. So, this implies, yeah, so that, and degree of G divides degree of F simply for this reason, yeah. So, divides degree of F. It is notice that G doesn't divide F itself, but G of T. Yeah, but degree of G divides it. Yeah, so that there is different way to put it. And if, of course, when you can extract roots of coefficients, then of course it is equal to to the power of so you can write down the polynomial that gives you this power, but this is it is different polynomial. Mm-hmm. So it is the thing is it is the problem is that it is this is the order how you do inseparable extension, first or the second. Yeah? So, and here you do inseparable extension firstly. Yeah? Mm-hmm. Firstly, you're doing separable extension, and then you, firstly you do separable extension, I'm completely wrong. Firstly, you do maximal separable extension, and then you do inseparable extension. So firstly, you add beta, which is a root of separable polynomial, and then you add take the pth power root, which is inseparable. So let me now define separable. So now we can. So now we can define separable extensions. Definition. E over f is called separable. Separable. If separable degree is equal to usual degree. Yeah, so in general you have inequality or even divisibility, and when the extension is separable, you have precisely this equality. And why I was so the reason is that in number theory it is convenient to talk about. So it will be convenient to use this kind of embedding in algebraic closure. That's why I'm recalling all of this stuff in this form. Yeah, simultaneously saying something about the theory, how the theory of the fields should look like here. Yeah. So then equivalent definition. Yeah. So E is called separable. So the extension is called separable. If any element is a root of separable polynomial, so separable means that it has no multiple root. If any alpha in the extension is a root of separable polynomial. And notice that yeah, so such a without which is without separable so irreducible polynomial without multiple roots.
So its definition of
separable
extensions for the upper one is the definition of separable extensions.
And yeah. I mean the equivalent. So now we're just this is actually this is definition of finite separable extension, but there is also a generalization of it to extensions that are not finitely that are not finite. Yes, so they are not finite dimensional spaces. There, the definition is a little bit different. And this, yeah. So the equivalence is the following. So suppose, yeah. So suppose we know. So let me call it definition 1 and definition 2. Yeah. So just notice that if Yeah, so the thing is so for example, if you have, take your extension and so how to reduce definition 1 to definition 2? You have to consider as before the sequence of elementary extensions. Yeah? So here I over here I minus 1 is obtained by adding some element, yeah? Alpha I. And notice that if your degree, so notice that second really tells you that, just if second definition holds. Yeah, so this implies that all your extensions come from a separable polynomial. Notice that if you pass to, remark that if you pass to sub-extension, then remark passing to sub-extension, so if you have E over F is separable, and K is intermediate extension, and K is intermediate extension, then E over K is separable. And K over F is separable. Yeah. So proof. So from definition 1, yeah. This you just write down E over K and times K over F. So this is written as E over F degree. This is equal to separable degree by definition. And separable degree is again multiplicative. This is multiplicative. This implies that, so this is definition 1, this is multiplicative. This implies that, and you know that this is divisible. We know that this is divisible by this, by E over K, yes. And this is divisible by K over F. So this implies that both of them are equal to equal. Yeah? So this implies that, let me write down inseparable degree. Yeah? So that inseparable degree is 1. And you could think of multiple, and the inseparable degree of KFF is also 1. So that means that the extensions are separable. Yeah? And here notice that definition 2 is clear for sub-extensions. Yeah, and yeah, so you see, yeah, so a priori, no, and if you know that they are both separable, then of course separability of the factors implies a separability of E over F, and vice versa. Separability of the factors implies equality for and separability of E over F. And but definition 2 is a little bit trickier. So definition 2 is evident, and if you use definition 2, yeah, so any element is separable. Yeah, so that clearly all elements of K are separable over F in particular. So K over F is evidently separable. And E over K is less evident. Yeah, so notice that alpha is a root of E. It is separable over F. So this means that if you look at the reducible polynomial for alpha over F is smaller field. Yeah, so if you enlarge the field, the irreducible polynomial can decompose. So this is so it is divisible by irreducible polynomial of alpha over the field K. And since this has no multiple roots, then this has no multiple roots. So this has no multiple roots. And this implies that this one has no multiple roots. Okay. So this yeah, so and now let us prove equivalence of the definition. Yeah, so now we can notice that so here we know that this all extensions for factors. Yeah, so if you know that big extension is separable, so just E over. So E over F is separable by definition 1. Yeah, this implies that I plus 1 separable degree is equal to I minus 1. Yeah. So I elementary extension, and this implies that polynomial is separable. Polynomial that of alpha I over E minus 1 is separable. And so sorry, this is this is not the. I'm sorry. This is this. I wanted to say that in definition two. Sorry. So suppose we know the definition one is done differently. So suppose E over F is separable in the sense of definition one. Then you have extension. So consider the extension, the sequence of elementary extensions. So so by definition one, we know that all intermediate of them are separable. Yeah. So this implies that E I. So the precisely the degree of the extension is equal to the corresponding degree. So, сейчас. Нет, я не то сказал. Сейчас. Давайте. Сейчас заново, извините. Сейчас. Ну, чтобы четко сказать. Сейчас. Yeah, so suppose our extension is separable in the sense of definition 2. So any element is separable. Yeah. So this implies so definition 2 in particular says that so as we have derived that sub-extensions of so if you have E. So any sub-extensions are separable. Yes, so you have E. K F. So this means that E over K is and K over F is separable by definition 2. So by induction on the degree, it is separable. So induction on degree it is separable by definition 1, but still there is a base of induction. The base of induction is when you cannot decompose the elements in the intermediate extension. But if you cannot decompose this, so if so base of induction, actually you can always decompose this by the following, by considering elementary extension. So base is just take K equal to F, where you have added one element, alpha. And by definition 2, this is separable elementary extension. So we know, since it is separable and elementary, we know that this is separable in the sense of degree. Yeah?
What do you mean by elementary?
Elementary obtained by one element, by adding a root of a reducible polynomial. So this is precisely what is written here. So this means that so this means that this extension k over f is equal to separable degree is equal to a degree of the polynomial. Degree of irreducible polynomial of alpha over f. And vice versa. So suppose we are separable in definition one. So definition one, so separable. So then it is clear that so you have to prove that for any alpha e, it's a root of separable polynomial of separable polynomial. But this implies that the previous remark implies that f of alpha is separable extension. And this implies again that it is elementary. This finishes as upstairs. Yes, so k of f is equal to k of s separable. So in a sense of definition one. And definition one says that this degree is equal to the separable degree, and this one is equal to degree of a reducible polynomial. And so this means that a reducible polynomial doesn't have multiple roots. No multiple roots, as we have studied this case. So the thing is that you should only know how just this elementary, so how these notions vary in the elementary and the extensions and the taking sub-extension, and just so how you take this extension and this extension. Yes, so if you know that E over F is separable, and vice versa, if you know that these two are separable, then composition is separable. And now let us move to normal extensions. So normal extensions. So normal extensions are the following. So definition. So the E over E over F is called normal. Yes, over K. Is called normal. Yeah, if if you have the following, this extension is not is called normal if all inclusions, so all sigmas embedding of E into algebraic closure of K have the same image. So have the same image. Meaning, yes, so if you have sigma and tau, two different embeddings, the embeddings itself can be different, for example, but the image can be the same. For example, you can embed just so image of sigma is equal, yes, to the image of tau. Yeah, for example, you may think of the field, so conjugation gives you this kind of thing. Yeah, so you may have trivial embedding and conjugation. Yeah? For example, you can take I and take minus I. Yes, so you can, and you can map a square root of -1 to I in complex numbers. Yeah. Or you may map it to -1. Both of them generate the same field yes, over R, which is C. But they have, as embedding, they're different embeddings. So this implies that you can consider, so you can compose in this direction. Yes, so they have the same image, so you can factor through image. Yes, so you have here maps by sigma to image of sigma, which is image of tau, and you can take, for example, pre-image of tau to map it to E. So this gives you automorphism of it. So this is automorphism. So in general, you have, since you have, moreover, if you have trivial embedding, you can compose it with automorphism, and this will be different embedding. So this implies actually what? That the group of for general extension, so you have the set of automorphisms. So the group of automorphisms of E. In order to you have inclusion of this this set to the set of embeddings. So set of inclusions. Set of embeddings of E inside K bar. Yeah, so in order to do this, you just fix one embedding and start twisting it by automorphism. Yeah? So you see, and you will get different embeddings. So definitely, these are just so the set of embeddings is decomposed under the orbits of automorphism group. Yeah? And the automorphism group acts freely. So this is the so automorphism group. acts freely on the set of embeddings. So you decompose. So embeddings are decomposed into the orbits of automorphism, and then this number is the number. This means that number of automorphisms divides the number of embeddings. The number of embeddings and which divides the degree of the field.
So, from what you said that automorphism acts freely.
You can take embedding
Uh-huh.
and twist it by automorphism. You will get new embedding.
Yeah, that's.
So just take
And
phi.
by free, you mean automorphism that saves k.
Yeah, automorphisms. Yeah, yeah. Thank you very much. This should be written over here. Yeah. So there is a special notation for it. So that phi acts automorphism. And if you take sigma, you can compose first by automorphism and then by sigma. Yeah? And vice versa, if you have already embeddings with the same image, you can reconstruct automorphism. So you see that automorphisms are acting freely because it is a new embedding. So different embedding. Because the embedding is the map, that is, we consider it as a map. And you see that this really explains notion of normality and separability. So that they are saying that, so separability says that you have equality here, this is separability. And normality is equality here. And alternatively, so we have to finish. So alternatively, normality is, so let me put it as an exercise. So prove that normality is equivalent to the following. So just you take any collection of polynomials over k and add all of their roots. Or you can take one polynomial over k and add the roots because you can take a product. Yeah, so you can take collection of polynomials with coefficients. So f1, fk inside k of t. And for the field, E is obtained as by adding all roots of the system. So of course by taking product you can take only one polynomial, which is not which is not reducible, but anyway. So the reason is that
What do you mean with this exercise? So like E
So,
over A is normal if
если только если вы берете любой набор полиномов, ну то есть это свойство расширения.
Ага, то, что
То есть как бы что ну точнее так, ну я неправильно сказал. То есть если взять любой набор полиномов и его добавить, то все его корни, то
E будет нормально.
да, то Е будет нормальным. Давайте я так напишу. So, давайте два утверждения. Первое, что so then E is normal. So if E is obtained as a union of all roots, then E is normal. And in other direction, if E can be obtained this way, if E is normal in the previous sense, yeah? So this is A, this is B. Yeah? So E is normal. Then if E is normal, then if you take any polynomial, any irreducible polynomial, then for any f which is irreducible over k, if you add if one root belongs to the field, then all so that means that all roots, so either f is reducible over E, over E. So it stays reducible when you consider over E. Or you add with one root, you add all roots. So or all roots belong to E. То есть либо он полностью разложим, либо он не приводим.